All right, thank you so much for having me. It's wonderful to see everyone here. Thank you so much also, Simon, for the wonderful introduction to my talk. We're going to be discussing this question that actually got me into astronomy. And I wanted to start with that. Here's a 90-year-old human life in weeks. Every square is a week of your life. And for the first 5 years, I wasn't really sentient. But then once I really hated physics. I wasn't going to do anything in physics because my dad was a physics professor. I hated it. And so I said I was going to do accounting or something else. And then I found that really boring. And I ended up in a physics class. Then once I started at U of C, along with Simon, we were in the same program. I said I would do anything but astronomy. I really didn't like astronomy. And it's so funny here now that here I am a professor in astronomy and Simon is president of the Royal Astronomical Society. So I guess I shouldn't ever say I will never do something. Then I did a gap year of travel. Sorry, I'm just gonna, is that going on? Hello? Oh, I killed it. No, hello? What's going on? Okay, let me try this other one. Hello? No? Yeah, there we go. Because I kept moving my head and it would go away. All right. I did a gap year of traveling and I went to a conference and I sat in on a session of how we could detect life on another planet. And I was just hooked. I realized for the first time that this is something that could happen in my lifetime, in my career lifetime, that we are nearing that technological sophistication. So then I ended up doing a master's and PhD in astronomy, though I said I never would. And I did a fellowship at St. Andrews in Oxford, and then JWST launched. And this is the first telescope that might be able to give us a hint of this answer, which I'll talk about. And now I'm a professor in astronomy at York U of Toronto. So it's really nice to be back full circle in Calgary, where I started my academic journey. Hopefully, before I end my career, we'll actually have an even bigger mission, which will be able to detect life on more planets, many planets. First, I just wanted to start with this image of Earth. This image was taken by Apollo 4 on November 9th, 1967. And it is the second color photo we have of Earth. And this is really what we're going to be thinking about today, is if aliens were looking at our planet, they could tell that there's life here, and we want to do that for other planets. This is a beautiful image of Earthrise. I recommend tobyorg.com/earth, where he has a lot of reconstructed images that are just simply beautiful from those early Apollo missions. So as promised, today I'm going to be discussing, are we alone in the universe, and how can we actually find out scientifically? So we've had the search for extraterrestrial intelligence. We've been looking for signs of intelligent aliens with radio telescopes since the 1960s. But so far, we've been met with silence. We haven't had the hello Earthlings to the call from afar. We haven't had any definitive evidence of life. And so I want to ask the audience, who believes there's life beyond ours in the universe? Great. A large number of people, the majority of people. Now, the second question is, when I said life, what do you envision? What comes up in your mind? Do you think of aliens or aliens? Small microscopic signs of life. So when I'm talking about aliens, I'm really talking about that second kind of life. Because when we think about how do we find life on another planet, we think about what is the dominant form of life on Earth, and it is actually microscopic life. It's microbes. Even in your body, you have about as many microbial organisms living in you as human cells. And so this is what we're going to be trying to find on another planet. We're going to be trying to find microbes. And if we were looking at Earth, as we did for the first time when Voyager turned around and took this 6 billion kilometer selfie of our planet, this famous pale blue dot image, what we see is we can break apart that spectrum of light into different colors, and we can actually tease out what's in our atmosphere. So this is the light coming through our atmosphere. We can see the different colors that make up that light and see signs of life in our atmosphere. And we do this because each element and molecule has a unique spectral fingerprint that's unique to that atom or molecule, and that is how we're able to then see what is in our own atmosphere or the atmospheres of other planets. So by doing that, when we take this pale blue dot image here and we break it apart into its different wavelengths, we see signs of vegetation, we see signs of oxygen, ozone, water, carbon dioxide, methane. And these all indicate that we have a global biosphere and a living planet. We've been finding other planetary systems since 1995, and we've now found just thousands of planets. We have beautiful images of our universe, such as this billion-star photo of our Milky Way galaxy. Of course, you've also probably seen the Hubble Ultra Deep Field, just showing how many galaxies there are in our universe. This image was taken in about 1 million seconds, and Hubble's, for context, is about $1 a second. So this image here is about $1 million. And what we see in it is all these tiny points of light are an individual galaxy with hundreds of billions of stars. And this point on the sky was about the size of a grain of sand held at arm's length. And within that, they found 3,000 galaxies the first time they made this observation. And when they did it again, they found 10,000 galaxies. Just in that size of a grain of sand is that many galaxies. So this is the first time we realized just how big our universe is, how many hundreds of billions of galaxies there are with hundreds of billions of stars. So, as you know, space is really, really big. We often think of the Earth and the Moon, something like this. This is not to scale. This is actually to scale. Here's the Earth, here's the Moon, and we could fit all of the solar system planets end to end within that distance. So I do recommend, if you haven't come across this before, I love this website. It's called If the Moon Were 1 Pixel, a tediously accurate scale model of the solar system. You can scroll through it and it gives you fun facts along the way of, how many movies you could watch on a trip to Mars, etc. And it just gives you a sense of how empty space is and how vast it is, even our solar system, let alone going to the nearby star. I also really love this YouTube video. It's the Hubble Ultra Deep Field in 3D. It more explains that image that I showed earlier and just how big our universe is and how groundbreaking that image was. All right, but let's get back to the topic of today's talk, which is how to find life on another planet. So first we need to find exoplanets, solar systems around other stars, and look for planetary environments that are suitable for life. And so here I'm going to be focused on exoplanets and what does this mean, suitable for life? So first, I'm going to argue that we need to look for places that have a surface. Perhaps life could exist in some Jovian gas giant atmosphere, and that there's certainly life that's hypothesized that could live there. However, we don't know how to detect such life. Everything on Earth requires surface, chemistry of water and rock interacting. And so this is where we're going to first look. And then the other thing we're going to focus on is liquid water. And I'm going to go into why liquid water, because that's one of the most common questions I get, is why are we looking for these sorts of environments? So the liquid water habitable zone is also called the Goldilocks zone, because if you are too close to your star, then the temperature is too hot on the surface. The water would evaporate and it wouldn't be on the surface of the planet. If you're too far away, water would freeze out and it would be a frozen planet. But there is this annulus around the star that is possible then for liquid water to be on the surface of the planet. And this distance will change depending on the star. So for stars that are bigger than the sun, the distance is further away. For stars that are smaller than the sun, the distance is much closer in. And this is where we are going to first take a look. It doesn't mean where life could possibly exist, and I'll get more into that in a second. Because this habitability word is something that's a bit of a swear word in astronomy communities. There's a lot of division over this because people argue, well, life could exist in other parts, so why do we use habitability? Or we're just using it to try to have a press release. Or astronomers sometimes will make a press release saying that they've found a planet that's in a habitable zone, and then the press release will say this planet 100% has life. These sorts of sloppy press releases have really divided the astronomy community and to people not really trusting this work. So I want to talk to you a little bit about why that is and what you should do when you're looking out for these sorts of things in the news. So, of course, habitability and a habitable zone both has nothing to do with life. Life doesn't need to exist in these places, but it also has everything to do with life, because of course we define it based on Earth life. So the first point here is just because the planet is in the habitable zone doesn't mean it's habitable. And just because the planet is habitable doesn't mean it has life. So you could have a planet with water and all the conditions for Earth-like life, such that if you were to send life there, our life would survive. But it doesn't mean that the origin of life ever happened in that environment. But what the habitable zone does do is it helps target selection, because remote detection of these biosignatures requires surface life interacting with an atmosphere. Why is this? So you could imagine that there are other habitable environments. You know, habitability is complicated. There are so many factors that go into it, and all of these things could play a role. We could have things with the stellar system, different types of magnetic fields and active radiation. You could have things with the rotation or the surface or the climate and the composition, tectonics. All of these things could play a role in habitability, so we can't necessarily learn all of those about exoplanets. Furthermore, we know in the solar system, many places are habitable in the classical sense. Europa is a prime example. Here's a schematic of Europa. You have 10 to 100 kilometer thick layer of ice, and then a liquid water ocean. This liquid water ocean is in contact with rock and minerals, and there's tidal heating, so there's energy there. This is a classically habitable environment, and it's been habitable for 4 billion years. So if life could evolve there, it could have persisted for a really long time. And this is absolutely a place we should look in our own solar system. However, it is close to us, and we still can't tell with telescopes whether there's life on Europa or not. Because if there is life, it is buried under this ice layer. It's here, and we can't see. There's no atmosphere for us to look at the way the light interacts with it to see those signs of life. So what I'm going to argue is this is a great place to look in the solar system, but it's absolutely horrible place to look for an exoplanet, a moon around a Jovian planet in another star system with a bunch of ice and water underneath it is just not something we're going to be able to do as astronomers for the foreseeable future. And when we think about where life could exist, one of the most extreme examples of this, of course, on Earth are extremophiles. Life finds a way. Once maybe the origin of life is really constrained. What do I mean by this? Maybe the conditions that give rise to molecules forming these complex patterns to give rise to life might need a very small environment, we don't know. But then once life gets hold, at least on Earth, it goes everywhere that liquid water is possible. And so you see that life has found a way to exist in the hydrothermal vents with extremely high temperatures and pressures in the deep ocean. You see it in near boiling hot pools in Yellowstone. You see it actually between the ice crystals in Antarctica, because between those ice crystals, there's salt in that water, and it keeps a liquid water layer, and then the microbes live in that layer. So wherever there's liquid water on our planet, we see signs of life. And my favorite extremophile, of course, is tardigrades. Who knows what a tardigrade is? Oh, some of you are going to get very excited now. Tardigrades are the best. So tardigrades, also called water bears or moss piglets, are complex life. They're up to 1 millimeter in length with 8 legs and 4 to 8 claws. So they're an animal. They're polyextremophile and they're complex. So what does this mean? They can withstand temperatures to well below freezing, near 0 Kelvin, to above boiling. They can withstand pressures 6 times the deepest ocean trenches on Earth, and they can withstand ionizing radiation 100 times what humans can withstand. They've actually taken tardigrades and put them outside of the International Space Station in a great experiment for Doctor Who fans here called TARDIS, Tardigrades in Space. And these tardigrades actually lived. They brought them back in 11 days later and then rehydrated them, and they started to animate again, eat, and have babies. So tardigrades are amazing. We've been trying to kill them for as long as we've known about them. We've tried to starve them for over, I think now 50 years. Without food or water, they're able to enter this chrysalis state and just stay hibernated until the conditions become right again for life. And they can dry out to within 3% or less of water, only to later rehydrate, forage, and then reproduce. So tardigrades are an example of a great form of life that could exist on another planet or in our own solar system if it were to have gone there. And we will certainly look for such life, such as on these planets, Europa is a classic example, Mars. Those are environments in our solar system that actually are classically Earth habitable. They have liquid water or had liquid water, or maybe in the subsurface. But Venus, Titan, these are environments that are really unlike Earth. I don't know who has heard about the phosphine plagues of life on Venus. A few people, right? I won't go into it too much. If you want, we can talk about it in the Q&A or after the talk. But Venus represents a really weird place, and it doesn't seem like life could exist, or even indeed a lot of chemistry. But if it's there, it's certainly fascinating. And Titan is a place with liquid ethane, methane lakes. It doesn't have water, so in a liquid form. So if we do find life on Titan, it would represent a completely different biochemistry. But these are places I think we really need to look. We have to go and search our solar system in order to see if there's weird life out there. But when we're thinking about exoplanets, we're going to be limited. So we can know a lot about the Earth and the solar system, but we can only ever know a little bit about exoplanets. Right now, we can get their mass and their radii to maybe within 20%, which gives us their density. But what we can do is we can only know a lot about a few planets, but we can know a little bit about a lot of planets with exoplanets. So what exoplanets allows us to do is to get that statistical representation, a statistical understanding of potentially how habitable environments evolve and are in the universe and how many there are. And that's what we're going to try to do. So the habitable zone is only helpful for target selection. We have thousands of exoplanets that we've found. We want to look for life, and so then we want to prioritize which planets to look first. And that's basically what the habitable zone does. It allows us to say, could we recognize maybe what's happening in this planet's atmosphere? Yes, let's search there first. But it doesn't mean that that's the only place life could exist, or the only place life does exist or could evolve. The other thing I really think is interesting about the habitable zone is the carbon cycle is a thermostat on our own planet. We've had liquid water on the surface for nearly 4 billion years on Earth history, even though the sun has changed in brightness by about 30% over that time. And this is due to the carbon cycle on our planet. So we could try to actually measure this on other planets and other systems and see if the same sort of geological cycle is present there. And so here, we have the TRAPPIST-1 system. We have these planets that are all Earth-sized within the same system, and 3 of them are within the habitable zone of that star. And so we can start to see, does the planet on the inner edge have less carbon dioxide, and does the planet on the outer edge have more carbon dioxide? That would be a first step to see if does this thermostat, this carbon silicate cycle, work in other star systems like we see it does on Earth. So these 3 planets, like I mentioned, are a great first target. They are all going to be observed with James Webb, and in fact, some of those observations are coming in this month. So we're going to start to understand what's happening on this very exciting system that's not very far from us. And what I love about the TRAPPIST system is, say you're on the surface of one of those habitable planets, the size of the other 2 planets would be about the size of our moon in your night sky. So just like you could see surface features on the moon, if you were on one of these habitable planets, you can imagine these other Earth-sized planets next to you. You could maybe even visually see with your eye signs of continents and oceans and vegetation with your naked eye, should you be in this planetary system and should this planet have life. Right now, we found almost 60 planets so far that are potentially habitable, and these are ones that certainly we will be looking to follow up with the upcoming missions. So that's step one, that's finding these planets. And then the second step is looking for where liquid water could exist. And why? When we think about what does life need, it needs food and water. So it needs energy, something that it can use to do the chemical processes that are fundamental to life. And it also needs water or another solvent for that chemistry to happen. So why water? Solvents are needed for chemistry, and water is a polar molecule, which means that charge difference pulls apart other molecules and allows it to do chemistry, which is one of the reasons why it's a good solvent. Water is also weird. It has this polarity which helps it bond really strongly, and the strong bond makes ice an unusually strong molecular solid. It also has this high surface tension, and that causes water to rise through vascular plants. It also allows raindrops to form ice floats, and then we have a water cycle on our planet. Water also remains liquid over a much wider temperature range than other molecules. Also, but for me, I think the most compelling argument of why water is everywhere we look in the universe. We see it on Mars, on the moon, in the interstellar medium. It is truly everywhere. And this is one reason why I'm very optimistic about our first search to look for water-based life. So we want to find biosignatures. And when we think about biosignatures, first we have to understand, well, what is life? And this is actually a harder question than we might think. Life is really weird. You know, we find life everywhere, as I mentioned. And so they found microbes that were dormant up to 50,000 years in these underground crystals that were still able to be revived. And even more weird, they found microbes out of 100-million-year-old seabeds that were dormant, and they were able to revive them. So life is just truly beyond a lot of our expectations and what we're learning about these sorts of extremophile life now. But when we think about, well, what is life? We could try to describe its characteristics. We could say, well, it grows, it replicates, it metabolizes, it evolves, it displays complex behavior. But all of these things can be done by things that aren't life. Crystals grow, computer programs replicate, forest fires metabolize, planetary systems evolve, and lightning and tornadoes display complex behavior. And so you might say, well, what is water though? Before we had the atomic theory, the definition of water, nothing was really sufficient until we knew water was H2O. Back then, we might have said, well, water is wet and clear, but so are some oils. So with only one example of life, are we really in a position to fully define life? And so that's one of our problems. So there's many definitions out there, though. Scientists don't stop with that. And there's about 48 or so commonly used definitions of life, but this is the most common, and it's NASA's working definition of life. Its life is a self-sustained chemical system capable of undergoing Darwinian evolution. So this assumes that it's chemical, not say AI. It assumes that it's self-sustained and it's not capable of undergoing evolution to evolve and adapt to its environment. And I'm just going to show this video because I find it terrifying, but also instructive to see how life evolves even in a short time scale. So this is a big agar plate that's several feet across. And this is, they put E. coli on the sides here and then have different levels of antibiotic in, so like times 1, times 10, times 100, times 1,000 in the middle. And you can see life evolve and break through. And it actually does this convergent evolution where it finds the same solution many times. So you can see some breakthroughs here and here. So it's evolving simultaneously different breakthroughs to break through the antibiotic barrier here. So now it's populating that times 1. It's already just blown through that times 10 on this side. It didn't even really pause. And then it's soon going to be in the middle of the plate, which, you know, is a bit terrifying. This is why MRSA and these other evolutionary problems are really difficult for us, because life is able to repeatedly find ways to overcome antibiotic resistance. And then see, this is the center where it's times 1,000 times that antibiotic. So it just shows us real-time evolution happening. And when we think about viruses, one thing, we've lived with COVID now for how many years? One fact I came across that just really also blew my mind is that there are 1 million times more virus cells, or they're not really cells, but viruses on Earth than there are stars in the universe. There's 10 to the 24 stars, there's 10 to the 30 viruses on Earth. That's crazy to me, anyway. Also, if you guys are interested, I really recommend this terrifying and very interesting podcast about fungi. It links together what dinosaurs and the extinction of dinosaurs and fungal resistance, and it's very fascinating. It's 30 minutes done by Radio Lab. It's really excellent. All right, so when we think about, going back to astronomy, when we think about this path of non-life to life, so we don't really know how that happens. We're trying to figure out this with origins of life research and trying to figure out how did life evolve on Earth. What's the simplest life? Could we do synthetic life in the lab? And so there's this great quote that I like. It's a long way from slime to Mozart. But we actually know how to get from slime to Mozart pretty well through Darwinian evolution. There's clear steps in the fossil record that show the adaptations and how you get from single cellular to complex life and so on, and how that complex life evolves, and you get the evolution of the eye and all of this. It's something that we more or less understand. So I would say this other researcher made a point in contrast to this, and he said, well, it's a long way from HCN to slime. We don't know how to go from a molecule to the first living cell. We don't know if it's a series of stepwise steps where you have something that's a little more alive than something before as you increase complexity. We don't know if you need to become really complex and then all of a sudden you're alive. Or if it's more of a smooth transition and those steps have just are not present on Earth anymore with all of our complex machinery of life. Because even a microbe today is so complex compared to what early life must have been. So the first living cell, we know, did not just fully form with all its complex chemical machinery. We know it must have arisen in a series of steps, with metabolism, early proto-metabolism, early ways of doing information transfer, and we have some ideas of how that might have happened. So there's basically two strategies for finding life in the universe. We can look at our solar system, and we can look on exoplanets. So there's lots of cool places to look in our solar system, and I think that we could take bets on which one will actually maybe find life on a planet first. And then, of course, exoplanets, we're going to be really dealing with this fuzzy pixel problem, where we're just data limited, and we have very little information about what's happening. But be that as it may, I'm an astronomer, and so exoplanets is where I spend most of my time. So we can think about, what does Earth life produce when we first start to think about how could an alien, if they were looking at our planet, tell that there's life? So you can see the spectrum. Here's the solar spectrum. This is the visible light with the rainbow. And then this is Earth's spectrum down here in these two humps. So this first hump is the visible reflected light. So that's the sun's light comes in, bounces off the surface, and goes back out. That is the visible part of the spectrum. And in that part of the spectrum, you see signatures like oxygen and water. But then you have this second bump here, which is the thermal emission. The thermal emission is the light that lands on the surface of the planet. It heats up the planet, and then gets re-radiated back into space. And that is the thermal infrared part of the spectrum. And you see signs of methane, CO2, ozone, and water. And what's interesting here is you can see that there's 10 billion photons of light from the star for every single photon you get from the planet. That is a huge problem, signal to noise, because you have so much light from the star. You have to try to block that out and tease out what the light is from the planet. It's just an incredible problem. But in the thermal information, it's about 1,000,000 to 1, which is still hard, but it's better. So this leads us to think about, could we find biosignatures around other stars? And this is my research. So this is actually what I do. I model the atmospheres to see what kind of wavelengths do we want to look at, what resolution of telescope do we need, how big of a telescope should we have in order to make sure that we can find the signs of life. We're going to be paying $10 billion. Let's make sure we build a telescope big enough to actually answer this question. And so my specific research is, how does the star impact the atmosphere? Because stars come in different sizes, they have different types of radiation, How does it work? How does the atmosphere and the spectral features influencing the atmosphere to change the biosignatures and how we might be able to detect them? So as I mentioned, if we have this pale blue dot image, and what the strongest features that an alien astronomer looking at Earth would see is oxygen and methane. These two gases indicate life on Earth. And this is because both of them are produced in large quantities by microorganisms on Earth. You have oxygen produced by plants as well as microbes. You have methane also produced by microbes. But you could get them separately without life. So you could get oxygen with UV light breaking apart water or CO2. You could get methane abiotically with volcanoes. So either of them separately does not indicate life. But what you see on Earth is we have biology pumping large quantities of both gases into the atmosphere. But if biology were to turn off tomorrow, if all life were to be gone, those two gases would react quickly in the atmosphere and they would no longer be simultaneously present. So it's the presence of both of those gases together which indicate life. Neither gas separately indicates life. So I want you to remember that if you take only one thing from this talk, that's the thing you should take away from, because you're going to see press releases of, we found oxygen in an exoplanet. It means there's life. Well, did they also see something that wouldn't be present on those timescales like methane? Something that's a reducing gas. And you have to have both of those together. So the oxidizing plus reducing gas is the strongest biosignature we have come up with to date. We cannot think of a way to make that without life. So we have these two challenges. We have this technological hurdle, and then we have this interpretation hurdle. And what's really cool is, the technological hurdle is huge. As I mentioned, this 10 billion column of photons to the star. And that's a bit like trying to find a firefly in front of the spotlight, but imagine the spotlight is on a different continent from where you're observing. And so that is the signal problem. It's actually about 100 times more difficult than this. And that's what we need to do with telescopes. And what's amazing is we're really nearly there and able to make those that signal in the next few decades. We can see the technological improvement already with some of the images in our own solar system. So this is what we knew Pluto looked like in 1930 with this fuzzy pixel of light. That's basically what the best image we have of an exoplanet right now is about like this. Then with 1994, we had the Hubble Space Telescope, and we had a slightly better image. Then with some improvements to Hubble in 2003, we get a bit better. Now this is a bit unfair because this is a flyby mission. We can actually now see snow-capped mountains on Pluto. So these are the sorts of technological improvements which have happened. My absolute favorite images are from Jupiter's Juno image orbiter. They've just taken these incredible high-resolution images of Jupiter, and we're learning so much about the dynamics that are happening in the atmosphere of Jupiter. We can actually see clouds on Jupiter. You can see the clouds here. These ammonia ice clouds, water clouds on Jupiter, and we can actually image them now. So with these sorts of telescopes that are happening, I think of this as a timeline of excitement. We have so many cool telescopes that have been in development that are finding exoplanets, and we're going to have more. So right now we're entering the era of JWST. We're having the first atmospheric detections with the James Webb already. And so James Webb it's going to be harder for small planets. So this is, a giant planet, and this is a model for a more Earth-sized planet. So it's just very, you get into signal problems here, but it will be able to do it for a few planets. So James Webb is mainly going to be looking at gas giant planets, Neptune-sized planets, Jupiter-sized planets, and it's just going to be able to do a handful, maybe 6 or so of Earth-like temperate planets. So we'll get a hint, but we're not going to get the answer with James Webb. Then we'll enter the Plato and Ariel era. These are ETH emissions in Europe. Plato will determine the densities and compositions of a lot more exoplanets, and Ariel will be the first mission dedicated to exoplanet atmospheres. Still, it'll mainly be planets that are bigger than Earth. So if we want to find signs of life before I die, which is the only reason why I entered astronomy, because otherwise I thought astronomy was useless, we're going to need something bigger. So we're going to need something like LUVAR HAVEX, is now what I call LUVEX in the astronomy community, or something like life. This is a mission team that I'm part of in Europe called the Large Interferometer for Exoplanets, where it's a formation flying with 4 telescopes to do this, and then this is more of a visible mission. And both of these together would give you a wide wavelength coverage, which would allow us to make some really cool observations of exoplanets. So we have these technological hurdles. We have these space-based telescopes like James Webb. We have the large ground-based observatories like the European Extremely Large Telescope, or the other ones that are also large, all just ELP. These are the ground-based ones that are say 30, 40 meters in size. And between these two, there's just trade-offs between the science you can do with these types of missions. So with space, what you can do is you can get a low-resolution spectra of the planet, and that helps you get the abundance of the molecule. Well, that's important because you want to know how much of a molecule you have in the atmosphere, more than just is it there or not. But we can't do that from the ground, but we do see a higher resolution spectra. And so we can see the presence of even more minor species. So in space, we can only get low resolution of the real dominant gases that are present in the atmosphere and get an idea of how abundant they are. But from the ground, we can do high resolution spectra. And you can even see the presence of isotopes, which just blew my mind when I first learned about this. So high resolution spectroscopy is where the planet is orbiting the star, and that Doppler shift of the light of the planet changing actually makes the line go like a sinusoid over the spectrograph. And so you can see these those little sinusoid lines, that's carbon monoxide going, and those black lines are carbon monoxide in our own atmosphere. So we can actually see through our atmosphere where there's molecules present in our atmosphere, but we see the drifting of that line across our spectrograph in the planet orbiting this other star. And that allows us to make this. So this is the cartoon of what's happened. So we see these lines drifting across the spectrograph from the planet orbiting the star, and then we can make the observation of that molecule. What we do is this is a really high resolution spectrum. We can match a template of that molecule, and when we see a peak, we can see that that's matched for that molecule. So it doesn't tell you the abundance of the molecule, but it does tell you it's there. And like I said, it can actually tell the difference of just one neutron. So this is an isotope, so say with hydrogen, you have a proton and electron. With deuterium, you have a proton, a neutron, and an electron. And you can actually, with this high resolution technique, tease that out. So this is because the high resolution spectra is different enough between those two things. So this is carbon monoxide with carbon 12, and this is carbon monoxide with carbon 13 in orange, and those are the high resolution spectra. So you could actually see that in an exoplanet atmosphere, which I just never thought was going to be possible in my lifetime until I heard about this in science. So this is already possible now with iRes Plus. It was delayed, these sorts of observations due to COVID, but I'm really excited to see if we can start to find that this year. And we can maybe find heavy water, HDO, in the nearest planet to us, Proxima Centauri, with this technique. So that's really cool. So the other thing though here, of course, is this interpretation hurdle. So those are some of the technological things and how we're going to overcome these hurdles with these upcoming telescopes. But then we need to be able to interpret what we're finding, because we're going to see this pale blue pixel. And how are you going to know if there's life there? It's not like you can go there and take a sample and see microbes moving around in your microscope. So there's really only one type of life detection which would be completely unambiguous. And that's this sort of SETI hello Earthling signal. Then you know there's life, it's been found. But otherwise, we're going to be arguing about it. And so I love this quote by Richard Feynman. He says, science is a way of trying not to fool yourself. The first principle is that you must not fool yourself, and you are the easiest person to fool. We want to find life. It's so easy to look at something. This is what happened with Venus, right? With the clustering of Venus, the scientists were like, oh, maybe it's life, and so then they made a preemptive discovery. This just is kind of an optical illusion to show us how easily our eyes can be tricked. These are all the same color ball. All of them, they're the same color. That's kind of wild, right? I mean, I know. I mean, you guys aren't responding, but I look at that and I'm like, no, it can't be. But like, if you start to, zoom in really far and look at the, RGB colors with your little color picker on your computer screen, they are indeed the same color, but I just cannot see it as the same color, no matter what I do. So this is part of the problem. And we've seen this before. If you've seen this image of the Cydonia region on Mars, this is a happy face image, or here, our eyes are just prone to see faces and things. And so when we first had this low resolution image, our eyes were like, oh man, maybe this is a sign of intelligence on Mars. They like left this face for us as if they were going to look like humans anyway. And then when we took a higher resolution image of the same region, the face disappears. So this is a problem with low resolution data. It's also probably the same thing that happens with Oumuamua, that interstellar loper, right? We just have low resolution data, so we can interpret whatever we want to into that. And of course, we want to see life, and so some scientists have claimed that as well. So this interpretation hurdle is where I spend most of my time as a scientist. This is what I find the most interesting, because again, I really want to find signs of life before I die. I don't want to just make the detection and say oxygen. I want to actually say this comes from life. And so when I often talk about this, I think this is what people think about when I'm talking about we're going to find life on another planet. They think it's, Pandora with tall blue creatures with tails. What theorists like myself claim we're going to find is this really easy to see spectrum with all these clear features of life. And the reality is it's not going to be that. It's going to be a fuzzy pale blue pixel. There's going to be lines with big error bars, and many models might be able to fit that line. And so we're going to be arguing about what it means for a long time, as you can already see with some of the detections that are currently being debated. So how to get over this interpretation hurdle? We could look for unique biosignatures. These are things that only are produced by life. The pro is there's no known false positives. But the cons there is they're usually really rare, and they're limited to a single microbial species, normally an evolutionary quirk. So there's no reason to think those would be present in other planets. They're produced in very small quantities, and we don't even have the spectra for most of these molecules. Of the 16,000 possible molecules that could exist, we only have spectra of inequality for 0.04% of them, which is not a great place to start looking for molecules then. We could look for alternative biosignatures. That's not very Earth-centric, but we have no idea if those chemistries exist, and we can't even tell if those chemistries exist in our own backyard. And as I mentioned before, water and CO2 are abundant in the universe. Carbon is more abundant than silicon. It forms more complex chemistry, and water is polar and has unusual properties. So this is where I think for alternative life, let's look at the solar system. But then for finding life on other planets, we're really going to be back to searching for Earth-like life. The pro is we might understand what we see. Oxygenic photosynthesis uses light, carbon dioxide, and water. These are all abundant in our universe. So this is why often people ask me, well, why oxygen? Why do we focus on oxygen? And oxygen, oxygenic photosynthesis, the organisms that make oxygen, use water and CO2 in combination with photons. And that's it's the most successful biomass building product on Earth because it uses those very common constituent molecules to run its metabolism. There's no shortage of places to look. There's 40 billion Earth-like planets in the Milky Way. The con is that all of these classic biosignatures as single gases have geological or photochemical false positives. So we can't use any of these molecules alone to indicate life. And we could be fooled, even if we find both of them together. We can't visit the planet and look at alien kangaroos jumping around on the surface. So we need multiple gas detection. This is going to be expensive. And a lot of these false positives are the strongest for MWARs, where the UV is really important for that star type. So this is what I tend to focus my efforts on. So these are all the stars within 10 parsecs. These red dots are all the M stars. So M stars represent 75% of the stars in our galaxy and around us. And so these are the first places we're going to look. You could ask, why aren't we on an M star? Well, the problem is that you have different UV environments as you go from hotter to cool stars. And UV destroys some biosignatures like methane, making it harder to see potentially in the atmosphere of a planet orbiting that star. And it produces other biosignatures like ozone, making the signature perhaps easier to see for depending on how much UV there is. So when we think about M stars, we know that Kepler has found that about a quarter of M stars have a habitable planet. So they're great places to look. The problem is M stars have these huge flares, and these flares could rip apart the atmosphere. They could destroy life on the surface. These planets might not even have atmospheres. And so this is the problem for M stars. This is an example of what could happen on an M star. So M stars have this really high energetic phase. This extreme ultraviolet light could break apart water into hydrogen and oxygen. Hydrogen is really light and escapes, and then you're left behind with an O2 atmosphere, and there's no water on that planet anymore. So that's an example of a false positive mechanism for getting oxygen and why oxygen alone isn't a good biosignature. These are all the known false positives for oxygen and ozone. Most of them are most prevalent for M stars, and all of them depend on the UV radiation. So this is what I'm saying when I say that we really need to understand the UV environment of our stars. This is why. So the UV matters, and no single gas is enough to claim life. And that's the main thing I want you to take away from this talk. The strongest biosignature to date is an oxidizing plus a reducing gas. So I don't think I have much more time, right? How much? Like 5 minutes? Okay. So I'm going to touch briefly on this concept also of Earth going through time, because planets are unlikely to be like modern Earth, right? We don't expect all planets to look like our own planet, and Earth itself has changed. It's gone through this Hellenic phase to an Archean phase with these tidal pools, to snowball phases, to the Jurassic period, where there was even in some parts of Earth's history, we have even larger amounts of oxygen and dragonflies that are like a meter in diameter. So when we think about Earth, Earth is not just one planet. It's actually many planets as it's gone through its biogeochemical evolution. So one thing that I like to think about is if we were to break my talk down into an hour and we were to think about the history of life in this hour. So we have the formation of Earth at 0 minutes, about 4.6 billion years ago. We have the origin of life about 9 minutes into this hour, somewhere around 3.9 to 4.4 billion years ago. We don't actually know when. We have the oldest signs of life at 3.5 to 3.8 billion years ago. Some people even argue 4.1 billion years ago. The older we get, the more tenuous that evidence is. That's 14 minutes into the hour. We have oxygenic photosynthesis, definitely around 25 minutes into the hour, or 2.7 billion years ago, at least then, probably earlier. But it took a long time. It took 47 minutes into the hour. Only in the last billion years or so have we had multicellular life. So most of Earth's history has been single-celled organisms. Then we have land plants only a half a billion years ago, 53 minutes into the hour, and humans, anatomically modern humans that look exactly like us, those are in the last 250,000 years ago, or the last second of this hour. So if we look at the Earth's atmosphere as it's changed over time, there's been more carbon dioxide earlier in the atmosphere, more methane, and then oxygen has largely risen in 2 distinct steps. And so we can start to tease apart, well, what are the broad atmospheric states of Earth in its history, and could we put those around other planets? So this is kind of the bonus for the scientists in the audience. I'm going to show some scientific plots here, which are going to get a little crazy, but this is for those who are going to stay with me here. So what I did is I took Earth through history and I put it around different stars, some hotter, some like the sun, and some cooler than the sun. And this is what you get. So you see the pre-life in the top bar here. These lines are F stars. These are hotter stars going to M stars, the cooler stars. So that's the black line going to the red line is the hotter to cooler stars for a pre-biotic planet. And then as the second plot comes up here, that's after the first rise of oxygen when we had 1% our current concentration after the great oxidation event. And then after the Neoproterozoic oxidation event, we had 10% of current concentrations of oxygen, and then finally the modern atmosphere. Okay, so let's break this apart. What is most interesting here? I think this ozone feature is super interesting. Because it pops out even really strong. Look how strong and deep that ozone feature is for those hotter stars. with very low concentrations of oxygen, only 1% of modern concentrations. But what's really interesting here is it's completely overlapping with that CO2 feature. So if you had a planet with a lot more CO2 in it, you would maybe not be able to tease apart whether that planet has ozone. These features would just overlay each other and it'd be very difficult to tease them apart. As you start to increase your oxygen, you start to develop this ozone feature for a higher number of stars. And then, of course, for the modern Earth, you can see it for nearly every single star type. But what we want to see is not just ozone, right? We want to see methane. If you've been with me for this journey, we need to see both of those gases together. And the methane feature is actually not easy to see in our modern atmosphere. We can still make it out. It's easier to see in these earlier phases of Earth history. So I did some other work with a student, Yui Kawashima, and she calculated how we could detect oxygen or methane with LUVOIR. And here is with low concentrations and increasing to like 1%, 10%, 50%, and then current concentrations. And these contour lines are the number of hours. So for low concentrations, it takes 300 hours. That's a lot of time in the most optimistic scenario. But it starts to get much more easier for these higher concentrations to detect oxygen, which is why people want to fly this mission, because you can actually start to see different concentrations of oxygen in the atmosphere. But detecting methane would be much harder. So here we can see that methane for the earlier epochs is quite easy to detect, but for modern Earth, it would take over 10,000 hours, and that's just not possible with a telescope that we would be launching. So we would not be able to detect with LUVOIR methane and oxygen together, which is what we want to see ideally. So we're going to need that other mission that I told you I'm part of. Like, you know, if you have $10 billion, please see me after, and we can talk about how to make that happen. So we have these technological hurdles. As I mentioned, we have this first opportunity to overcome this technological hurdle this decade with James Webb and these large ground-based observatories. But then we have this 25-year horizon where we're going to fly even bigger telescopes. And that's really what I'm excited about. And I hope that happens before the end of my career. Then we're going to have this interpretation hurdle. We want to see the difference between different types of terrestrial planets, be able to tease apart their spectra and find out what's in those atmospheres and try to see if we can understand what's happening on that planet. You know, we're just one planet amongst billions in our own Milky Way. And so we just make a very small space in this universe. This is the James Webb Deep Field with all of the countless galaxies that are present. Earth has been also on its own journey. There are so many different types of atmospheres that a planet could form, and Earth is only one example of that. Here with Earth-like life, we might see things like oxygen, ozone, methane, water, carbon dioxide. But also there can be other combinations. This is the Archean early atmosphere. If we see these gases, we might think also there's life because of the simultaneous presence of carbon monoxide with methane. There might be other combinations of gases that could indicate life. There's been hypothesized that ammonia in a hydrogen-rich atmosphere would indicate life. There's also probably a lot of other weird stuff which might indicate life that we just don't know yet, but we're going to try to figure it out. We could also see potentially failed biospheres, something where you have the prebiotic molecules necessary to form life, but life never took off on that planet. Hopefully, though, we're going to be able to tease apart those when we start to get some statistics. So what I want to leave you with, though, is even if we find out we're not alone, will we be satisfied? Because what I'm talking about here is detecting microbes. Will that be enough? You know, even if we detect something complex like a ladybug, would that be enough? Or do we really need to detect this intelligent signal in order for us to feel satisfied? So even if we're not alone, would we still be lonely? Thank you.
Well, thank you very much, Sarah, for such a wonderful, wonderful presentation. We're going to do our QA now. So we're going to take questions from the crowd here at the Calgary Public Library and from the people online. And I realized that the poll did not launch. So I'm just going to launch that poll for all of you people online. If you have the opportunity, please work through that poll and we'll look for some hands up here at the Calgary Public Library. And also for those of you on the online feed, please put your questions in the question and answer field, and I will ask those here tonight live. So.
This one for running in the audience, if you have a question for Canada, and one of us will come towards you.
Yeah. So yeah,
Just look at me to run.
there's a question.
We're just getting a runner here.
It seems that a lot of things are coming together quite nice. At the same time, a lot of new technologies, given that, for lack of a better word, cow parts are really difficult to extract. But that there isn't any real and known technology at the moment to find them. Are you hopeful? Because you seem so passionate, and will you be satisfied with not finding, maybe not even not intelligent, but just how do you feel? Do you think that science will come up with new discoveries, new ways of finding life without having to rely on the, deconstructing the fingerprints of cow parts for lack of a better
Yeah.
phrase, yeah.
Yeah, thank you so much. Yeah, so will I be, for lack of a better word, satisfied with detecting microbial, like tenuous evidence of microbial life?
Yeah.
Yeah. This is longer working. Hello. Okay, there we go. I think, so for me, my journey as I've gone through my academic career is I really thought we would definitely find life in my lifetime back in the day, and I thought we would have a more clear sign of yes or no. And now the more that I've learned about it, the more I realize how difficult it's going to be, and that we're not going to probably know with 100% certainty. We might know with say 90% certainty, but there's always going to be that like bug of what if we miss something? Because we can't go there and actually look for life on the surface of the planet. And so I still find that exciting. I think we can do it in a statistical way. But in that way, I am like, while I don't do research on this, I'm more optimistic for finding life in our solar system. I think there's a better chance for us definitively finding life on Mars or finding life in Europa. And then that would answer that question. So that would be harder to see if it's a second origin of life, or if it was just transferred between our planets. So then there's pros and cons to that. Long story short, I mean, if I could be cryogenically frozen and like woken up in 1,000 years once we have the Star Trek Enterprise or something, that'd be great.
You and me.
Thank you for the question.
All right, we'll take a question online. Somebody hears that the James Webb Space Telescope got some damage during the deployment, and that for the most part, they were able to work around it. But I'm curious, does it impact the results of your work at all?
No, actually, the James Webb is performing very well and in some ways better than we expected. So often there's slight problems that happen in any telescope launch, but we can often work around it by doing different detector sort of techniques or pipeline changes in our data pipeline to make it still give us great data. The main thing that I was terrified about was the unfurling of the solar shield. That was a mission critical component. If that wasn't to happen, we would not be able to do the science that I'm interested in. That would be a problem.
Great. Another question from the crowd.
So all these markers that we're looking for are in the atmosphere. Are they all restricted to carbon-based life? Like if there is like a silicon-based or some other element-based life, would the markers be completely different?
Yes, excellent question. So yes, we are limited necessarily, I would argue, to carbon-based biochemistry because we don't know what the other alternative chemistry would form as a biosignature. So we can, until we know if silicon-based life, or if we create it in a lab or something like that, and we start studying, oh, this molecule might be a biosignature, then we might be able to extend that to exoplanets. But right now, that's all so hypothetical, and we're not there yet. We don't even know how carbon-based life started, that we just can't, which is why I go back to that point, though, that carbon is abundant, CO2 is abundant, water is abundant. It seems to be more abundant than any sort of other type of life, that are other types of biochemistries out there. I think an interesting chemistry would be something on Titan, where you have liquid ethane, methane. These are hydrocarbons. The hydrocarbons don't form as much complex chemistry, so I'm just not as excited about that. So I would say, yes, we are looking for carbon-based biochemistry, necessarily because no one's been able to come to biosignature for something that's not carbon-based biochemistry. There's a whole bunch of questions I see up here on this side.
Okay, we'll take one more from the crowd and then one from Zoom.
These are just pretty videos for you guys. I'm enjoying them. You want to zone out,
Hi, and great presentation, by the way. So my question is I know that you guys are trying to find life in exoplanets, and the James Webb Telescope is a great tool for it. My question is, are you guys considering in seeing these exoplanets having moons? I feel that the moons play a very important role, the size of the moon, and would James Webb Telescope be able to detect these moons and see how big they are, and more or less promoting a better possibility of finding life in the planet, right?
Yeah, excellent question. So there are certainly some of my colleagues, David Kipping, for example, is really interested in finding moons. We don't really understand, is a moon better or not for life? I mean, all of it's very, from our own perspective, we have a big moon relative to our planet size. And so it stabilizes our climate. So we think that's great, for life. But that's a very Earth-centric viewpoint. We don't really understand how life would evolve on other systems, and maybe those systems be like, well, you don't have planet that's just going all over the place. Like that's, how do you get cool, interesting vacations or something? So we don't really understand this question, but we are trying to find moons and see if we can get a sense of that. Moons are very hard to see, so we're kind of limited to relatively big moons right now, and so we want to get a sense of the the whole statistics of moons, but definitely people are looking for moons. Actually, and also moons are one way you can get a false positive of oxygen and methane together. Could you? That's like a whole other topic though. So if we do, we would want to rule that one out with moons.
We'll take a Zoom one. Okay, we've got a great question on Zoom here. Great talk, thanks. Instead of looking for absorption features in an exoplanet atmosphere, could we instead detect emission lines, notably the oxygen green line from aurora? Detecting green aurora on an exoplanet would tell us that the planet is geologically active, has a magnetic field, and has abundant oxygen, which might indicate life.
Yeah, so we also can look for emission features. Looking for aurora features for an Earth-like planet is out of our technological horizon right now. It's just very difficult. But there's emission features for, say, bigger planets that we're looking at, and we'll cut our teeth with those observations and hopefully in the future be able to do it for the smaller planets.
Great. Question at the front.
Thank you for your presentation. I was just wondering, what are the wavelengths are we looking at? Are we looking at terahertz radiations, microwaves as well, or just a visible spectrum?
Yes, great question. What wavelengths are we interested in? We're primarily looking in the visible and infrared, just because the contrast ratio between the star and the planet is visible to us. So there's features also in the microwave, but the light emission from, or the microwave emission from those planets is so faint that we just can't see the transitions there as easily. So we look for the wavelengths that have the most molecular features. That's mostly in the infrared is the best place to look. I can bring the microphone here to this question.
Great.
Hey there. So in the water feature, could water be something else? Like, could it be like, something else? Like, could it be like hard or like in a force of rock?
Yeah, so when we are looking for these features like water, we're looking in the atmosphere. So it's something that's volatile. When we say volatile, it's something that is able to be present in the atmosphere, not necessarily the water locked up in rocks. So we wouldn't be able to see rock minerals in or water in that form. It would be hard for us to also see ice, water on the surface. We're really limited to what could be present, gases that could be present in the atmosphere. So we would be looking for H2O in the atmosphere. And H2O gives really strong imprints along with methane and carbon dioxide. And those are the dominant gases that you would expect to see.
Take one from Zoom after this question.
Since all the planets are so far away and moving at different speeds, would redshifting and blue shifting have an effect on the scales?
Absolutely. So do you remember what I showed with that high resolution spectroscopy and the Doppler shift of that planet orbiting the star? So that's the Doppler shift of just the planet going around the star, but you also have to consider the Doppler shift of the whole system. So the system is, moving towards or away from Earth, and so you have to factor that in as well into the observation and subtract that out. So yes, the Doppler shift matters to certain types of exoplanet observations, particularly this high resolution spectroscopy technique. There's a question up here, I saw.
Yeah, see feedback.
Thank you for your presentation. So I would like to ask your opinion about two theories about why we couldn't find alien civilizations. One is called the gray filter. It says that when a civilization develops to a certain stage, it's gonna destroy itself, maybe in a nuclear war or global warming. And the other one is called a dark forest. It says that there are civilizations everywhere, but they are hiding themselves. Because the universe is a dark forest, and those civilizations are like hunters carrying guns. So any civilization that explodes itself will quickly be eliminated by others.
Yes, who in this audience has read the Three-Body Problem trilogy? Okay, not enough is what I'm getting from this. You all should go and read it. It's one of the best trilogies I've ever read in my life, especially the third book, just blew my mind. But this has popularized this dark forest concept. Yeah, I mean, we don't know, right? We have one example of life, so we have no idea. And one thing that we, like on the optimistic side, we've become ourselves less violent over time, right? If you look at some pre-agricultural societies, there's sometimes a death rate like 20% due to violence. And, even with World War I and World War II, the death rate per as a rate of our population has declined over time. So maybe as, contrary to that, as species evolve in their social evolution, they become less violent. We don't know. So that would be maybe one argument against the dark forest. Of course, with the nuclear threat with Russia and Ukraine right now, it's easy enough to imagine that we could just completely destroy ourselves as well. On the flip side, it's really hard, I think, to eliminate humans from the planet, even in that scenario. There's a really horrible movie called Virus, I think. It's in the common domain of movies. You can download it from the Wikipedia page, and it goes through this whole scenario about basically all of humans being wiped out. And at the end of it, there's just 25 people left. And I was like, that can't be possible. You wouldn't have enough genetic diversity. But then I looked up the research on it, and indeed, it doesn't take that many humans. It's about 50 to 80 or so humans that are needed to have enough genetic diversity to repopulate the planet. So you can have an incredibly tight bottleneck and not destroy humans. And so I think if you were to remember things like the scientific method, you would, within a few thousand years, kind of be back to where we are. So even in really apocalyptic scenarios, I think it's going to be difficult to eliminate humans from our planet. And so there's this alternative theory that is once you reach a certain level of intelligence, it's actually you can self-sustain yourself forever. Basically, you can move on to different planets and start to think about ways to prolong your civilization. So I mean, it could be that that's true, but I also think there's enough evidence within our own society to have a more optimistic take.
Let's take some Zoom ones. All right, let's take a couple Zoom questions here. I think that the work you are doing to identify the uncertainties and limit the false positives is extremely important and adheres to the essence of the scientific method. Do your work results so far make you think that more traditional extraterrestrial life like radio signals will be more likely to identify life conclusively?
Yes, so I do think the hello Earthling signal would be by far the most conclusive evidence of extraterrestrial life. And there's this breakthrough initiative for SETI Breakthrough Listen. They're collecting as much data as SETI used to collect in a year within a day now. And so we're able to look at a much wider swath of frequencies and areas to start to answer this. And so Jill Tarter is this scientist that Ellie Arroway is based off of in Contact, and she has this analogy I think I heard from her where with SETI we've looked at basically the equivalent. We've taken a glass of water, we've scooped up a glass in the ocean, and we're like, well, there's no whales in it, so I guess there's no intelligent life out there. And there's a whole ocean, right? And that's about the equivalent of the frequency space that we've looked at with SETI. But within about, I think by 2050 or 2060, then we basically looked at the whole ocean. So I actually think we're going to be able to have more or less a better answer within our lifetime, hopefully.
Great. Thank you for that. Compared to some other sciences like biology, physics, geology, etc., astrobiology is relatively new. Do you see this field growing? Does something like AI make it a less viable career path?
So I think AI makes any scientific field more viable because we're able to do different types of science with AI, better data processing. Astrobiology isn't per se a scientific field, it's a merging of scientific fields. It's looking at all of these fields together. Science doesn't care about our silos, of having physics in one building and chemistry in another building. Science and life, it just is. It's a process on our planet that it evolves. It has geology, it has physics, it has chemistry, it has biology. So I think in that way, that's what drew me to it, is it really is science happening through all the disciplines at once. And I wish when I was an undergrad, and I see a lot of my physics undergrad majors here from Calgary, I wish I could take more different science classes. I was really like physics only, and I didn't take geology, I didn't take biology. And if there's any young scientists here today, I would say definitely take them all, because that's where the interesting findings are happening. They're at the edges of these fields right now.
Why in the panspermia theory, Mars is the first candidate for any life possibility?
So panspermia is this idea that life could have evolved on another planet and been transported. So there's a lot of interplanetary transfer between Mars and Earth, more than other places in our solar system. That's primarily why people are looking at panspermia from Mars. Also, Mars was habitable before Earth was habitable. So there's some idea that life actually started on Mars and then was transported to Earth, and then got going here and took off. Also, we've definitely, if Earth microbes can live on Earth, we've contaminated Mars with our roots and whatnot. So this is a possibility. This is why I think if we do find life on Mars, the next question is it different? Like, does it have a different origin than Earth life? Would be the most exciting part, because I think panspermia to me is not an interesting origins theory for, say, Earth or like the general life on Earth, because what we know of prebiotic chemistry is it happens pretty fast. And the early Earth had these conditions for the origin of life. So I don't think we need to outsource the problem to another star system. I don't think the origin of life is so difficult that it only happens once in a galaxy or whatnot. I talked to a very renowned origins of life researcher, and I asked him, like, what time scale do you think the origin of life happened on Earth? And he said like 10,000 years. That's like nothing. It's a flash. So I think panspermia is interesting within the solar system because we do have this interplanetary transfer. I don't think it's really relevant to transfer from another planetary system though.
Great. Let's take another question from the crowd. There's a hand near the front, just down there. Any other hands for
There's one in the
future?
back. I saw
Okay, we'll get to that one in a minute. So, right there.
Sorry, I'm hogging. Going from a single glass of water taken from the ocean to the entire ocean within 15 years, it's like mind blowing. Is there something you know that you're not telling us? If you had to guess, like why that might happen, what advances, like if you had to guess,
Sure.
what is it that made that not possible?
Yeah, exactly. So it's this idea, what I just mentioned with breakthrough listen, being able to take as much data in one day as we used to take in a year. It's things like AI data processing, machine learning processing, where we can just go through much bigger swaths of data. So that's sort of our processing capability is going up exponentially, and that's why you can go from the glass to the ocean in a fairly short period of time. I saw one hand way at the back if you want to, because I love it when people in the back are still engaged. All the way, yeah. No?
Oh, sorry. Just curious about if we have any signs of kind of like a water kind of a planet or any geosignatures or anything with them, kind of signatures which we got around. In the like any of our observations in the entire universe.
Yes, there's some indication that we've detected a water planet, GJ 1214b, I think, is the most likely candidate for it. So this is a planet where at the first we didn't know if it had water, if it had these high hazes of clouds, and then like further observations has narrowed some of this down. So water planets are really interesting, I think, not in the Kevin Costner movie sort of way, but they are, in some ways, astronomers get really excited about them because there's water, but origins of life researchers hate them because there's so much water. It's hard to concentrate molecules. It's hard to get the chemistry in a concentrated way to form like a high enough abundance to get reactions started. So a lot of people in origins don't think those places are habitable, actually, a water planet, but let's look. Let's see if we see any signs, and we'll hopefully that'll help constrain our origins theories on Earth.
Great.
Do you have a favorite origin of life theory?
I don't know. I've never gotten that question before. Thank you. I think it's really boring, but I like this idea of the RNA world because RNA can encode proteins and information. And so something that was just based on RNA first, I think is likely, that's a really boring theory because it's like the most accepted theory, but I do think it's a very elegant solution to this problem. Also, it was coined by just an amazing scientist, Wally Gilbert, who just puts us all to shame. He was an astrophysicist, PhD. Then he went on to develop biology and the main molecules used in MS and started the Biogen pharmaceutical company, but on the way won the Nobel Prize in chemistry and then did origins of life research. And now he's a painter in Boston area. So like this guy is just true Renaissance man, Wally Gilbert, and that's probably my favorite theory.
Great. Let's tie up a couple Zoom ones. So we'll tie up a couple Zoom ones and then we'll go back to the crowd. Are there or can there be radio telescopes directed at those exoplanets that appear habitable, as in your description, to ascertain intelligent life?
Absolutely, that's what SETI is doing, is they're looking at the habitable planets we're finding and trying to see if they can see any signals from them. It's like the first, place to look. So that's already being done.
Perfect. And we'll take one more from Zoom and then we'll go back to the crowd. How much does energy capture and storage play into the tools used? AI, sensor complexity and accuracy, deployment, image processing, spectroscopy, detail resolution, all of these play towards an energy management system, which for spacebound tools seems like a challenge of its own. Calgary, as a diverse and innovative hub and containing a strong energy sector, how could Calgarians working in these fields contribute better towards these common goals?
Yeah, it's an interesting question because it goes back, I think, fundamentally to this point of there's trade-offs between space-based missions and Earth-based missions. So on Earth, you can do things with much bigger spectrometers, higher resolution, and you can have much more advanced instrumentation. Space, you're really limited to what you can get into space and what is able to fit up there. And so that, but it's much better observing up there. So you always have this trade-off. I think one interesting thing that we might see in our future is moon-based telescopes. So that would be out of our atmosphere, and you could then have something that is more energy intensive on the moon. I don't know how Calgarians can get involved with that, but that's one area where I would go.
Great. Any more hands? There's one on the right there.
So it seems to me that a mission like LIFE is for James Webb Telescope. So how hard would it be to launch? And do you guys have any plans on maybe making it cheaper? Because there seems to be a lot of failure points in the mission that would have 4 telescopes.
Yeah, excellent question. So there's some pre-mission technology that we need to develop. And the primary thing we need to do is formation flying. You need to know where these telescopes are within a very tight distance, and you need to be able to calibrate that really well and get that really on point. So we have some development plans to do that with smaller scale missions to try to test that technology out before you fly the big thing. You need to make sure that technology is ready. That's the main thing that's missing. Everything else we more or less have. It is smaller. Each telescope is smaller than James Webb. So it'd be 4, say 2-meter sized telescopes. And, it is expensive. However, I think the US spent about the same amount on air conditioning within 2 weeks in the Iraq war. Elon Musk just bought Twitter for $44 billion. It's expensive and it's not expensive. I think it's worth doing for the questions that we might be able to get answered. But certainly before we actually spend that money, we're going to have some technology confirmation, primarily around television.
Hello, thank you. I heard of recently, well, not recently, but this idea of flying way out past Pluto, I believe, and using the sun's gravitational field for gravitational lensing. I mean, it's a futuristic thing, but actually imaging, planets possibly or whatever, using that technique in our own solar system rather than galaxy, the galaxy clusters and all that.
Yeah.
Do you know about that?
Yeah, I'm not, I've heard of it, but just kind of at a popular science level, I don't really know its application to Earth-like planets. I think the first thing we're going to do, because as you mentioned, it's more of a horizon sort of far away idea, is we'll just be able to block out the starlight itself using a star shade or a chronograph. So you can fly something in front of the telescope like a star shade, which blocks out the star's light, and then you can directly take a picture of the planet. And I think that'll give us our first pictures of exoplanets. There's also this idea of breakthrough star shot, where you send a whole bunch of nanocams to Proxima Centauri and just, you hope a few of them are pointing in the right direction, and you send like thousands of them, and then you get like a few images you hope are actually pictures of the planet back. So that'll be really exciting.
You don't think the actual gravitational field of the sun would be enough?
Oh, it could do it. I mean, it'll definitely be able to do gravitational lensing. I'm just not sure exactly what science it would do. But if you could get out there and use the sun as a gravitational lens, you could do some interesting science. Yeah. So it's definitely possible. I don't know if it's gonna help us with Earth, like planets around other stars and exactly the application there. There's one down here in the middle.
I like your pants, by the way, they look really cool. My question, it's kind of a simple one, but it might be really hard to answer. Say you find those magic signatures like methane and oxygen and they're present together. What's next?
Yeah, open a very expensive bottle of wine. I would be really excited. I think that what I fear, I guess, is that people already think we found life. You know, so when I talk to a lot of people in the public, they think we're hiding aliens, or we've already found aliens, or we've announced the presence of aliens. You know, there's this whole like show us them aliens campaign with like the presidential election and whatnot. So a lot of people think that we've already found life, you know, and they think we've not only found microbial life, we've found intelligent life, communicated with it, and that this has already happened, or they think they've communicated with it. I mean, you get all of the above. So I think people are going to be really underwhelmed, you know, when we're like, we found microbes, and they're like, wait a second, I thought we're fighting aliens already in Area 51. So this, I think, to me, is like one of the tragedies of this field, is that because of conspiracy theories, as well as from bad press releases by scientists and scientific journalists who've oversold claims, that we won't meet this monumentous occasion in human history with the awe that it's due. So I think detecting that would be incredibly amazing, and it would be the most profound discovery of humanity, and people are gonna not care. So I think, I don't know, what's next is I'll try to convince people to care.
You can always join, say.